the velocity of the point here should be perpendicular to the radius vector from this point to the instant center. And what enables it to do that is that it is capable of moving in this direction with the motors, and it is capable of moving in this direction because of this particular wheel. So a rover like this, a wheeled vehicle like this, can be given any motion. So the most difficult thing with the previous one was parking. How do you park in a very narrow space? You have to go back and forth. Whereas in this particular case, you can move here and then you can move sideways into the parking lot. Okay, so that's possible. Okay, let me come to simple wheels but capable suspension. This particular rover here, the wheel vehicle here, is called a shrimp, and it has a very funny suspension here. The wheels are regular wheels. Okay. Now look at this climbing a step. The wheels are much smaller than the step size. A typical wheel is able to climb a step only if the step height is lower than the radius of the wheel. Okay, much lower than the radius of the wheel. Whereas here the step is much larger than the diameter of the wheel. This is able to climb it because this articulated suspension actually moves up and is able to attain configuration which enables it to climb. Okay. This was proposed for a planetary mission. It has not been sent. Other rovers have been sent, but the rovers which have been sent to Mars, okay, the Sojourner, Mer, Curiosity, have similar kind of suspension design which enables it to handle uneven terrain, uneven hard terrain. Because the other problem in planetary terrain is that it is soft sand. Getting stuck in sand is a big danger there. Now let me take you to another mechanism which is used in a walking robot. So what you see here is a robot developed in IIT Bombay. It has 6 legs. Each leg has 3 degrees of freedom that you can see here. This is the mechanism of the leg. What you see here is what is called a pantograph. Okay, so this is based on a pantograph. It is driven basically by these 2 actuators. If you drive one actuator, this will move roughly vertically, and if you drive the other actuator, it will move roughly horizontally. So these 2 motions are roughly decoupled. When you move forward, you don't have to move the center of gravity up and down. And this is the leg, and then of course the whole thing can be rotated about an axis like this. So you can see that here there are 6 of them all around, and this makes a walking machine. So this is another mechanism used in robotics, in walking machines. So what I wanted to show you was basically various mechanisms. But if you go back to our manipulator, if you are a designer or somebody who selects a manipulator for a particular task, then a very important question in front of you is which robot, which manipulator should you select? There are so many manipulators available with different mechanisms. So how do you make a selection? So to some extent the selection is based on, for the task, where all do you want the mechanism to reach? Okay, the end effective reach. So what is shown here are the shapes of the workspaces of the different robots manipulators that we saw, the serial chain manipulators that we saw. Rectangular, cylindrical, 2 cylindrical, 2 spherical. Okay. Now typically this spherical mechanism, in terms of being able to generate a large workspace for the total length of the robot, this is the most capable. So if you want a compact robot which can reach a large area, this probably is the most capable. This also, the other spherical also is fairly capable. Whereas a rectangular mechanism is the worst for that. I mean, rectangular, the Cartesian robot is the worst for that. But this typically is more rigid than this. Okay. Another important thing is not just the area of the volume of the workspace you want to reach, but if there are certain typical motions that you want to perform, and you can perform it with minimum number of actuators, then that is an advantage. You can lock actuators and you can move only one actuator. For example, suppose most of the motions are straight lines, and those straight lines are, let's assume, along one of these axis directions, then in that case the Cartesian robot is the best. Because you can lock two actuators and you can move one actuator in order to perform most of the motions. Some of them will require all three. Whereas for any straight line motion, all these will require motion of more than one actuator. Okay, not all of them. In this case, up and down, and this motion can be performed with this. In this case, actually radial motions can be performed with this. So the selection would also depend on the typical kind of motion that you want to perform. Okay? I just wanted to tell you about some of the considerations that we use in selecting actuators, selecting manipulators, in designing that. Okay? So I'll now wind up this recapitulating. So we saw different types of manipulators. Mostly what we saw were serial chain manipulators, particularly the mechanisms of that. There were a few parallel chain manipulators that we saw. And then we saw some mobile robots, the wheeled ones, and a walking robot, basically the mechanisms. So this is what I wanted to discuss in the first talk. Thank you. And if you have questions, I would like to answer.
So can you go back to the slide on the walking robot? I wanted to ask you what is the advantage of a mechanism where you had a cylindrical actuator as opposed to motors at the joints?
So one of the biggest advantages is that because of that linear actuator, so these are what are called linear actuators. These are actually made from motors. You actually have motors here, then you have a screw here, and there is a nut which moves up and down, which actually gives this linear motion. So the biggest advantage of that is that a significant reduction in speed and increase of force. Okay, and that is the biggest advantage you
also provide stiffness then, because it will be a worm gear without back drivability.
Yeah, actually in this case it is back drivable.
Okay.
So it is a ball and nut. It is a ball screw kind of a joint here, kind of a system here. So this is back drivable. So a disadvantage with that is that it has to apply force all the time to stay there. But the advantage is that you can have force feedback. So that if you measure the current, that can give you a sense of what the forces are.
Thank you.
So questions from the electrical engineers? In fact, something fascinating I find in robotics is that there are many electrical engineers who do better kinematics than many of the mechanical engineers. Okay, so they learn it enough, understand it, and there are very good researchers with background in electrical engineering who are working in kinematics. So what it means is that fundamentally your +2 geometry is enough for all this. Rest of it you can really read and understand. Yeah, any other questions? Yeah, this again is a very broad kind of a talk where just a set of mechanisms were shown to you. We are going to get into some calculations in the next, which will require a little more concentration. So, if there are no more questions, let me thank you for listening. We'll meet in the afternoon.
Thank you, sir. And participants will continue in the afternoon.